These are the symbols we are going to use in our virtual lab. They represent basic circuit elements spanning from voltage sources, resistors, capacitors, inductors, etc. Next to each element, you will see a key value. For instance, next to a voltage source, one will find the frequency or voltage. Next to a resistor or a capacitor, one will find the resistance or the capacitance, etc. More importantly, we're going to use something we call a virtual oscilloscope, or scope for short. Our scope has a very important function. It provides the voltage or current of a point in our circuit as a function of time. Scopes provide this information always with respect to a reference point, which is usually the ground. If we probe our scope where the purple arrow shows, the scope provides the voltage waveform from that point with respect to the ground, which essentially reflects the voltage across the capacitor. This voltage will be displayed on the top part of our screen as a graph between volts along the y-axis and time along the x-axis. Take a moment to understand this very important point. If we now probe our circuit where the green arrow shows, then the indicated waveform represents the voltage only across the entire circuit, again with respect to the ground. Let's examine the following scenario, which will help us understand how a capacitor, or cap, behaves. A 1-volt battery is connected to a capacitor and a resistor in parallel. This is essentially a resistor-capacitor, or RC circuit, connected to a direct current, or DC power source. The resistance is always present due to the wiring. Here we have nominally a resistor of 5 ohms. In this virtual lab, we will show the current going through the resistor with orange color, and the current going through the cap with purple color. This last argument, that current flows through a capacitor, may sound as odd, and indeed, from what we know as capacitors, it is odd. However, it is the famous Maxwell equations that explain why current can pass through a capacitor. This may require some knowledge outside your curriculum. However, it is worth a read. Please consult your lab manual for more information. Now back to our experiment. When the switch is closed, there is a very brief moment where there is current running through the cap. You can visualize this from the graph. When the cap becomes fully charged, the current across this branch of the circuit goes to 0 again, and the current then goes through the resistor only. The animation of our virtual lab replays automatically, so we strongly encourage you to study how the current and voltage behave. The takeaway here is that in a DC circuit, the cap is essentially treated as an open part of the circuit, since when the cap is fully charged, no current flows through. This animation will help you answer question 1 in your review. Many applications require the knowledge of the time that it takes a capacitor to charge or discharge. For instance, this knowledge is important to know how fast a battery can be charged. It is important to realize that a cap of capacitance C connecting to a resistor R in series needs time tau equals R times C to charge to 63% of its maximum voltage. In contrast, a fully charged cap will discharge by 37% after 1 tau. Take a look at your lab manual to figure out why this is. In order to measure this time constant, we need to use a step voltage instead of the DC voltage we used earlier. The reason is simple. We need to allow the cap to charge and discharge in order to measure this time interval. A simple application of DC voltage does not allow the cap to discharge as we observed in the introduction of this virtual lab. Let's set up our experiment. In this case, we use a source with frequency 10 milliseconds that is equivalent to 100 Hertz with a maximum of 6 volts. Observe the green line that represents the voltage of our entire circuit, and the purple represents the voltage of our capacitor. Notice that the voltage across our cap does not reach its maximum at the same time as the green line. This can only make sense since the cap does not charge instantaneously. The bigger the cap, the more charge it can hold, the longer it takes to fill it up. In this case, our RC is 500 microseconds. Now observe a couple of other things. The cap's voltage has the shape of the so-called shark fin. We can observe the same pattern from our real scope. The shark fin indicates that the cap has plenty of time to fully charge and discharge. This happens when the time between input voltages, which is essentially our frequency, is much higher than the RC constant of our circuit. In this case, 10 milliseconds are much more than our RC, which is 500 microseconds. The information in this image is needed to complete your report. Closely observe our lab scope and figure out which measurements displayed on the scope screen are associated to our RC constant. Now see what happens when we increase the resistor by about 15 to 20 times. We no longer observe the shark's fin, but rather a triangle-shaped voltage waveform. This means that the capacitor cannot fully charge or discharge since the RC is also much larger. As a rule of thumb, 5 times the constant RC is an adequate time so that the cap can fully charge or discharge. Note that by finding the appropriate combination of resistors and capacitors, one can modulate the shape of the output voltage, for example, a triangle shape. Let us now connect a 5 ohm resistor to a 100 microfarad capacitor in series and connect it to an AC source of 10 volts peak and frequency of 100 hertz. Now we are going to probe the voltage to the left of the cap. Again, this measurement is with respect to the ground, hence it reflects the voltage only across the cap. We are about to find out that the cap's presence introduces a major difference, at least with respect to our previous lab where we dealt with a purely resistive circuit. Here, in the green color, we overlay the voltage across the cap, and in the purple color, we show the voltage across the entire circuit. You can clearly see that the cap reaches its maximum voltage at a later time than the voltage across the circuit does. Let's give this lag a name. We are going to call it the phase difference between the voltage across the cap and the circuit. Let us also give this lag an algebraic expression. By phase, we mean angle, indicated as theta, that can be computed as the inverse tangent of the ratio between the voltage across the cap and the resistor. We're going to figure out a bit later in this presentation why theta is calculated as shown. We can understand from a physics point of view why this lag is present. It turns out that the reason is rather simple, and we have already highlighted it in the previous virtual experiments. Unlike the resistor, the capacitor is storing charge. Therefore, the cap needs time to fill with charge, and certainly this cannot happen instantaneously. And since charge is directly proportional to voltage, charge equals capacitance times voltage, one could say that the exhibited lag in the capacitor's voltage is a well-expected behavior. One could further argue that the greater the capacitance, the greater the lag. Let's test this hypothesis. We are going to increase our capacitance. This is one of the amenities that this virtual lab on RC can offer. You should notice that the voltage phase difference between the circuit indicated with purple and the cap indicated with green becomes greater as we increase the capacitance. The larger the capacitance, the larger the amount of the charge that the cap can store. Therefore, the longer time it takes to charge. The combination of these factors leads to a greater phase difference, as we earlier defined with theta. Of course, the opposite happens when we decrease our capacitance. Our previous hypothesis has been corroborated. Let's now test the same hypothesis in terms of frequency. We observe that increased frequency is followed by a greater phase difference between the voltage across the circuit and the voltage across the cap. The opposite happens when we decrease the frequency. But why would the frequency have an effect on the phase? The physical explanation will be given a little bit later, after we have examined the behavior of the current. We have seen how the cap voltage behaves as a function of capacitance and frequency in an RC circuit connected to an AC source. In particular, we observe that a higher capacitance leads to a higher phase difference. We also observe that a higher frequency has the same effect. There is another very important observation we need to make: the current. The resistor and the cap are in series, therefore they are run by the same current. Remember that the current does run through a cap in an AC domain. We will use our virtual scope to study the current in our circuit. Remember that the same current runs through the resistor and cap, since they are in series. Here we plot the current with orange, while we keep the same colors for the voltage across our circuit, purple, and cap, green. Note that the current maximizes when the cap is fully discharged. That is when the cap's voltage is 0. In contrast, the current is 0 when the cap's voltage is at its maximum. You can pause the video to observe this a bit better. This is an expected outcome, since we know that the current is defined as the differential of charge with respect to time as current equals charge over time. This result directly shows that the phase difference between the cap's voltage and current is 90 degrees. This finding has an important implication. Since the same current runs through both the resistor and the cap, and the current is 90 degrees out of phase with the cap, this means that the resistor's voltage and the cap's voltage are also 90 degrees apart. This last statement is in tandem with how we computed the phase angle between the circuit voltage and the cap's voltage, and directly stems from the fact that the voltages across the resistor and the cap are 90 degrees out of phase. Let us repeat the previous experiment where we change the capacitance and observe what will happen to the current. To make the animation less noisy, we will omit the waveforms of the voltage we discussed a minute ago. The current is shown in green color. We are going to keep the frequency of our AC source at 100 Hz and 10 volts peak. We gradually increase the capacitance. We observe that current magnitude increases. However, this has a limit. When a certain value of capacitance is reached, the current no longer changes. Let's change the frequency, but keep the capacitance at 100 microfarad. We will go from 100 Hz to 200 Hz, 300 Hz, and so forth. We will observe the same behavior as before. The current magnitude increases, but up to a point, after which the maximum current magnitude does not change. When the frequency is decreased, the opposite result is observed. Let's recap what we have found out so far. We have observed a dependence of capacitance and frequency on phase difference of the capacitor's voltage. Also, we observed a dependence of capacitance and frequency on the current through the circuit. These observations strongly suggest one thing, and only one thing: that the capacitor in an AC domain has a resistance. The cap's resistance is called capacitive reactance. We denote this with X sub C. Here, F is the frequency in units of hertz of our AC source, and C is the capacitance in farads. At this point, we have provided the physical insight of why and how the capacitor's presence affects the behavior of an RC circuit in the AC domain. Now we are ready to study a real circuit with both real and virtual measurements. In this example, we will combine all the previous knowledge and methodology we have developed. In this case, we have the elements of our circuit: a 10 ohm resistor in series with a 100 microfarad capacitor connected to a 100 Hz AC with a 10 volt peak. Note that for easier viewing, the cables and connectivity are not shown. In the upper part of the screen, the purple indicates the voltage across the circuit. The green indicates the cap's voltage, and the orange indicates the current running the circuit. Now look at the lower part of the window to see the items we have at our disposal in a real lab. These are a circuit board, a function generator, essentially our AC source, a scope, and a multimeter. Let's take the first measurement. Using the multimeter on the left, we probe the voltage across the resistor and read 3.678 volts. Note a couple of important things. The first is that the multimeter directly gives you the voltage across the resistor, unlike our virtual scope, which was providing voltage across the entire circuit. The multimeter provides an instantaneous average of the voltage across the resistor, which we call relative mean square, or RMS for short. We do the same across the capacitor and read 5.805 volts, also in RMS. Now let's try to fit these measurements in Ohm's law. First, let's remind ourselves what Ohm's law states for an RC circuit in the AC domain. We found that the voltages across the cap and resistor are 90 degrees apart. The voltage across the circuit can be found by using the Pythagorean theorem. Therefore, Ohm's law can be written as shown. This begs the question, which is a representative value from our measurements? The answer is simple. We can verify Ohm's law using RMS values that we measured with our multimeter. VR, relative mean square, is 3.67 volts. VC is 5.8 volts, also in RMS, and the calculation of the summation under the square root gives about 6.9, which is indeed pretty close to the RMS of our circuit, which is 10 divided by the square root of 2, that is 7.1. There is a small difference between 6.9 and 7.1 volts, but this can be due to the instrumentation accuracy. This is the first step towards building a trust relationship between our measurements and theory. Let's now examine whether our real measurements agree with our virtual scope. Take a look at the purple line that represents the voltage across the circuit. We know that we have inputted 10 volts peak from our function generator. Indeed, the maximum of this purple waveform corroborates that we have 10 volts peak. The green waveform represents the voltage across the cap. Indeed, the maximum voltage is approximately 8.2 volts. The RMS of 8.2 volts would be divided by the square root of 2, that is about 5.79 volts. We are in agreement with what our multimeter measured, that is about 5.8 volts. It is important to remember that the multimeter gives a temporal average of the voltage waveform. That is in many cases very handy, but at the same time it limits the information to one single unit. Now we will compute the phase angle between the cap and the circuit's voltage. This computation stems directly from our previous measurements with the multimeter. The computation of the phase angle returns about 57 degrees. We can double check that with our real scope. From the scope, we read that the time difference between the two maxima is about 1 millisecond. Converting 1 millisecond to degrees, we get 36 degrees. Accounting for the complementary angle, we get 54 degrees, which is pretty close to our previous calculation of 57 degrees. Note that the scope-based calculation of phase angle can lead to errors, since choosing the respective maxima of the voltage waveforms on the scope screen can be highly subjective. So far, we have made 2 voltage measurements using the multimeter, one across the capacitor and one across the resistor. We have also confirmed that our virtual scope agrees with our real measurements, and all voltage measurements are properly linked to Ohm's law. There is one more measurement that we need to corroborate: the current, and how this is employed in our measurements and the Ohm's law. Where can we fit current in our previous computations? Ohm's law states that the voltage drop across a circuit element is proportional to the current running it and its resistance. It is important to understand that Ohm's law does not discriminate between resistors, capacitors, etc. We do have a resistance for the capacitor, except we now call it capacitive reactance. Given that our capacitance is 100 microfarads and our frequency is 100 hertz, the resistance of our capacitor is about 15.9 ohms. Based on Ohm's law, we estimate that the current running through the cap must be the capacitor's voltage we measured, that is about 5.8 volts in RMS, divided by its resistance. This results in about 0.36 amps. This value should be the same if we computed the current solely based on our measurement of the RMS voltage across the resistor. The computation above confirms this. There is one more important thing to add. We are reminded that we have essentially two resistances in series. Therefore, we can combine these into one equivalent resistance that represents the entire circuit. We call this the impedance Z. Our impedance in this case is about 18.8 ohms, as the herein computation shows. We can use the impedance in Ohm's law to re-estimate the current of the circuit, which is going to be the ratio between the voltage of the circuit in RMS units divided by the impedance. This also returns about 0.36 amps. That is consistent with our previous estimations. But are our measurements close to our previous estimations of 0.36 amps? Our virtual scope registered a maximum current of 0.533 amps, which in RMS terms is 0.533 divided by the square root of 2. This equals 0.37 amps. We are also in agreement with our real measurements, since our function generator reports 0.36 amps RMS. Given the AC configuration, we estimated 0.365 amps. Everything seems to be in order. In light of the previous findings, we can now explain some of the observations which we left lingering. Increasing the frequency decreases our reactive capacitance, which eventually makes the resistance the determining factor of the impedance. When R is much greater than X sub C, the impedance is essentially equal to the resistance. No matter how much we lower the reactive capacitance, in other words, increase the frequency, the current will always remain about the same. In this case, we call this RC circuit a resistor-limited circuit, in that the current is controlled by the resistor. The opposite of the scenario will happen if frequency or capacitance decrease. In this case, we call the RC circuit a capacitor-limited circuit, in that the current is controlled by the capacitor. The so-called low-pass and high-pass filters are based on these aforementioned concepts. Let's quickly review the algebraic expressions we have used up to now. In the AC domain, a cap has a resistance. For an RC circuit in series, VR and VC are 90 degrees apart. We define the phase difference, the impedance, and the current. Consult your lab manual to see how we can work an RC circuit in parallel. We have concluded our virtual lab on RC circuits. You should be ready to address the questions in your report. Since you currently do not have physical access to the instrumentation, we have made these measurements for you. You can find this